So last time we started looking at our first new integral test to figure out the convergence or divergence of a series. I should have said series test. So let's review what methods we have to decide whether series are convergent and divergent so far. What do we have? A divergence test, which is really easy to apply, right? You can do it in your head most of the time. What else? The integral test is our new one. That's the heavy-duty, long one that you try to avoid if you can. It's not hard, it's just long. What else?
Telescoping method?
Telescoping series, yes. That goes back. Telescoping has a lot to it. Make sure you're clear on the theory. Shh. Make sure you're clear on the theory of telescoping. That also has like partial fractions in it sometimes, and it has the very basic idea of finding the limit of the sequence of partial sums. It's kind of a long sentence. Make sure you're clear on that, okay? And then we also have geometric, that's 4. So far we have 4 series tests. We're going to build to about 10. That's about how many there are in basic series. And sometimes multiple tests will work. It's just a question of finding the fastest one. You know, you want to find the easiest one to use. So today we're going to learn another test, which is super simple. It's probably the easiest one that exists, and that one's name is what? Harmonic and p-series. Really, let's just remember it as p-series. The harmonic series is the harmonic series. That is the harmonic series. Okay? The harmonic series is one that you should remember as the series that does something a little bit unexpected. A little bit, not too much. Okay? So, this theorem basically says what you can do with any series that's in the form of a ratio where the n, the index of the series, is to any power, p. This doesn't have to be an integer, it can be any power. If you can write your series like this, or you can like distribute your series, or like, you know, break off a piece and have that piece of the series look like this. If you can make it look like this, you can do the easiest thing possible, which is call it a p-series and decide if it converges or diverges immediately. Because if it's a p-series, if p is bigger than 1, it converges. You don't know what it converges to. The days of knowing what something converges to are pretty much over. If it's not geometric or telescoping, you don't know what it converges to. You could just say whether it converges or not. Finding what it converges to is much more difficult in most cases, okay? So we'll learn some methods for that, but you know, they're involved, so we're not there yet. So anyway, if p is bigger than 1, it converges. That should kind of make sense that bigger exponents down here might lead to convergence. Because why? It'll go to 0 faster and faster the bigger that p gets. Not thinking about the series, but thinking just about the sequence, right? And the order of magnitude and just the sequence, the individual terms in the sequence. Because the big idea I've been trying to get you guys to grasp onto that I didn't understand even in Calc 2. It's not a hard idea though. It's that if the growth of the sequence gets small enough, fast enough, when you start adding up the terms in the sequence, which is a series, it'll converge. If it doesn't add up so that the sequence, if the sequence doesn't get small enough, fast enough, you're going to keep adding more, and that's not going to be contained inside of a little box, like that little video that we saw where you're able to contain that growth inside of a box. Does that make sense? That's the idea. So, if p is 1, or between 0 and 1, what you're adding is getting smaller, but it's not getting smaller fast enough to be boxed. In other words, to converge. Okay? So that's the big concept. I mean, if you can grasp onto that concept, series, all of them are going to become easier for you. I didn't get it, and I still did fine in series. So, anyway, this, what's p? Because it falls into that case, right? What's p? 1. So the harmonic series is the most famous p-series, in other words, and it diverges. This guy is divergent. The reason I would give is because it is the harmonic series. Now there's all kinds of famous proofs using different tests and different ideas as to why the harmonic series diverges. I'm still going to try to find a new one this year, like a video where they show it geometrically or something so you can really see it good, like that other one that we saw. Because the other one that we saw, I think, was also, it was 1 over 2 to the n. 1 over 2 to the n, 2 to the n grows much faster than any order of growth like this, right? That definitely gets small enough, fast enough to be boxed and to hence converge. Okay? But, okay, this guy's in a p-series. Clearly, does it converge or diverge? Converges. Bottom's growing a lot faster than that one did. That shouldn't surprise you. Okay? So we'd say this guy converges by p-series. You do need to explain yourself. You can be brief, but you need to explain yourself and say it converges by p-series with p equals 2. Done. Okay? Number 3. Is that a p-series? Is that a geometric series? Is that what?
P-series.
It's a p-series. What? It doesn't look like the same. What do you mean? Ah, it's n to the 2/3. So it converges or diverges? Diverges. There we go. But what about the 7? The 7's screwing things up too, I thought.
Can't you just move a 7 out?
Yes, you can. Remember, sums work just like derivatives and integrals. You can distribute them across plus or minus. You can pull things out of them. They work just like limits, like these guys are doing right now. You can do that with limits, derivatives, integrals, and series. The only thing you got to be careful about is like products of quotients, right? That gets dicey with some of them, most of them, in fact. Cool. So this is equal to 7 technically times the series from 1 to infinity of 1 over, you guys said 2/3, we sure? 1/2 is square root, 1/3 is cube root. There we go. That looks like our p series right up there. So we're going to say that this guy diverges since p equals 2/3 is less than or equal to 1. So diverges, I should have said, by p series. If I'd have applied the divergence test, would the divergence test have concluded that that diverges? Take the limit of the sequence. What's it go to? 0. So does the divergence test also conclude that it diverges?
Yes.
No.
Oh, no, yeah, right.
The limit of the sequence went to 0.
So it doesn't, it's
Inconclusive. Inconclusive. Remember that word, inconclusive. The divergence test, in other words, failed to conclude any information that's useful. But p-series does say, yes, in fact, this guy does diverge. Okay, same kind of thing we could have said about the harmonic series up there. Harmonic series also fails the divergence test. Okay. All right, so we've looked at those 3. I had one more series that I wanted to investigate today. And also, before I erase this guy over here, we did this the other day, back in section 8.8. Where's this come from?
Isn't it the same as the
It comes from the integral test.
Yeah,
You had that problem in your assignment where you had to integrate the indefinite integral. Do you guys remember integrating this problem? I think I even went over some of it in class. And we looked at the integral from 1 to infinity of like 1 over x to a non-specific power. Didn't we do that one?
Mm-hmm.
And then we learned like at the end that it either, that integral, that improper integral either diverged or converged based on what p was. This is the exact same thing. So how do you prove this theorem? You apply the integral test to it. You apply the integral test to it, make sure the integral, the inside is decreasing, make sure it's positive, make sure it's continuous, do the integral problem that we did the other day, and that's what pops out. So p-series comes from the integral test applied to that situation. Done. So where did it come from? Not a crazy place. It came from the other thing in 9.3. So how about this last problem? Integral test. You sure? Let's try to do something easier. I don't want to do the integral test. Maybe you guys love the integral test. You might. It's cool.
we can do it by
Everybody likes integrals, but
we can do it
like.
by parts.
A natural
Because you
log.
have natural log and 1 over n.
But like parts, doesn't parts only work on like things that you can? I like how you're looking at that and saying it's factored. I like how you're saying it's like factored, Kylie. But like that's not a linear term or irreducible quadratic.
A log product would be
Does divergence test help you? No, because the limit is 0. It's inconclusive.
Well, you have like a derivative sitting
Yeah,
right next to
yeah.
it, so I feel
That's
like
why I said it.
Yeah, okay, so integral. You're seeing the integral right away. Great, but I always want to try to avoid it, so I'm just thinking through it a little bit before I try to do all that work.
Did you
So-
use the log product?
Wait, you
Move the n up.
could A be
Think
one
about the
over
order of growth. You've got n, and then ln of n is like smaller order of growth than n on the bottom, right? So you've got n, which if that was just there, it would diverge, right? But you've got n times something a little bit more. That little bit more isn't very fast growth, right? Because if it was like anything more than 1, if it was like 1 n to the 1.1, p-series would say converges. So is this enough to be 1.1? That's the question.
No.
Maybe. It's really hard to say. It's a tough question. So you guys are right. We're going to have to do an integral. So to do the integral test, remember, you have to check your assumptions. Make sure you do. If you don't, I'll mark the problem wrong. So you need to check that it's always positive. Is it always positive on 2 to infinity?
Yes.
Remember, here we're not going 1 to infinity. This says 2 to infinity. Big deal. Go 2 to infinity. That's the way you can modify the test. Is it always positive? Yeah. Right? We can just say that. Yeah. Always positive on 2 to infinity. Something like that, yeah? And I should say what's always positive. We could go this. Have good English. Okay? Alright, so is it decreasing? Show that 2 ways, right? Last time we checked it was decreasing with a derivative. And we checked to see if the derivative is always negative for 2 to infinity. You can also check the n plus 1 term versus that term and see if it's bigger. You want to do that this time instead? Okay. Alright, Gabe said check the n plus 1 term. So see if a sub n is smaller, or no, decreasing. Wouldn't it have to be bigger than the next one? Question mark? We can do it that way. Let's do it both ways just for grins, just for practice. So over here we have 1 over n times the ln of n. And over here we have n plus 1 times ln of n plus 1. Ooh, the fact that these are inside that natural log is kind of freaking me out. I don't know. Let's see if it works. I don't know. We might want to do a derivative, is all I'm saying. Alright, cross multiply. So the question is that true?
Yeah.
Kind of hard to draw a very completely conclusive statement out of this, isn't it? N is the same. If n is the same value from 2 to infinity on any of these, this is clearly bigger.
Yeah.
But it's not a proof, right? So maybe you could keep going with the algebra here and get a proof, but I don't know. I think you're going to have to be pretty darn clever with your algebra. That's why it's good to have 2 techniques. You guys know what I'm saying?
Could you,
Or do you have an idea, Gabe?
or, never mind.
I'm sure there's a way to do it.
Can
I'm
you
just
put
not
the
seeing
n
it.
up and then combine the 2 logs and then do the,
you could always like
Yeah.
split the.
Yes, Gabe's right. Can we do this? Let's do it there too. Plus becomes what in logland? It's times. Times. If I times by another n plus 1, isn't that going to just do this?
Yeah.
It's starting to get better. Can we e both sides?
You lost an n on the other side.
Did I lose an n?
On the
ln
ln
of
to
n,
the
yeah.
n. Yeah, it's ln of n to the n.
Then you can move down. Oh,
There's too many n's. Thank you. Nice. Nice. We can e both sides now, yep.
You would say
That's pretty
true.
conclusively
Yeah, you could
true.
say that that's pretty true.
Yeah, I agree. So that's enough evidence. You could even do things like this though then, right? Right? And go back to like this. And maybe try to keep going a little bit more. But that is pretty conclusively true. I agree with you guys. Very nice. The other test, remember, is I'd like to really see you do both. You'll be a lot better off if you do. If you run into something where you're like, take a derivative, make sure it's negative 4 2 to infinity, and you're good to go. Both, especially, don't forget about your derivative. Good practice to do some derivatives. Okay, so we're good to go. The integral test is something we can do on this function. We don't have any asymptotes in 2 to infinity, right? So it's continuous. So positive, decreasing, and it's continuous. Integral 2 to infinity 1 over x ln x dx. You guys said you knew what that integral was. What is it?
The natural log of the natural log of x.
Yeah.
Yes, ma'am. Because u is ln, the derivative's sitting right there. What's the derivative of 1 over u? Ln of u, ln of u. There we go. So, it's going to be equal to the limit as b approaches infinity of the natural log of the natural log from 2 to b, which is going to be the limit as b approaches infinity of the natural log of b minus the natural log of the natural log of 2. As b goes to infinity, that guy's irrelevant, so it stays there. If you put infinity into that, eventually you get infinity slowly. That makes it even slower, but eventually you're going to still get to infinity. So conclusion, that diverges, so that diverges. You want to say that. So we'd go over here and say since the integral from 2 to infinity of f of x diverges, the sum of a sub n from 2 to infinity also diverges by the integral test. Conclusion. There you go. So now you have 5 tests to look at series. See you next time.
Hedgehog.